I hope you can hear me well and you can see my screen, which should be saying Introduction to Compiler Concepts, which is the set of slides that I'm going to present today, this being the first lecture. Welcome to our class 6241, which is our graduate class in compilers, which mainly deals with the optimizations, the backend optimizations of the compiler, which is really in my opinion, is the foundation of software systems and provides a pretty neat and clean vehicle towards performance and many concepts that we are going to learn in this class. So let's first introduce ourselves, myself and Nathan. So I'll go first and then I'll ask Nathan to introduce himself. So I work in the research area of compilers. I've been at GT for almost 20 years. I do research in compiler optimizations on a variety of topics, starting with high performance systems, embedded systems, which is at the other end of the spectrum, and then everything in between, and also compilers. The concepts, are foundational in terms of program analysis principles, and those can be applied across the board towards areas such as security. So I do a lot of work on security, and lately my interests are focused on how we can leverage compiler technology in outside of a single program. So far, the technology has been used in terms of optimizing the performance of a single program when it just executes by itself, but that's no longer the case for a very long time now. The programs always execute in a shared environment, sharing resources with other programs and such. And in such an environment, can we do something about improving the performance and also security characteristics of the program and so on? Anything that you share leads to a performance consequence as well as a security problem. And so my interest is focused currently on can we deal with these two problems in a shared environment outside of single program execution. As we go through this class, later on you'll see that some of you will hopefully get very interested in doing something in this area, and if you have such interests, we can talk in terms of, but that should occur only in the later stages of the class once we really understand this area very well, and hopefully we'll be able to talk then in terms of what are the interesting research issues and what am I working on and so on. So with that introduction, let me turn it over to Nathan, who is going to be our TA and who also works with me. He's a PhD student. So let me ask Nathan to introduce himself and then we'll get going.
Hi, everyone. My name is Nathan Braswell. I did my undergrad at Tech from 2012 to 2016, and then went to work for GCRI, the Georgia Tech Research Institute, and then have last year started my PhD. I'm really interested in programming languages and compilers and new optimization styles and type systems and such, and I'm currently working with Professor Pandy to integrate machine learning heuristics to do better inlining as an optimization. So I'm excited to TA the class. I TA'd as an undergrad and really enjoyed it. So hopefully I can help you guys however I can.
All right, great. Thank you, Nathan. So let me now get going with our class in terms of a little bit of logistics, and then we'll dive into the first topic here, which is what you're seeing in the screen share setting. So if in case any of you have any problems or anything that you're not able to hear or not able to see things well, etc., there could be problems in terms of my side or your side, we don't know. If there is any problem from my side, of course, I will correct it. I'll see some little icon here which is rotating network connection disruptions or whatever. If there is something like that at your end, you do the same. In case you have any question or anything like that, I will pause in between. In a real classroom setting, it's much easier to do it, seeing you raise your hand and so on. I will do some pauses in between to take some questions from my end. And again, if you are not understanding something well, or if you are, want to get some question in, please raise your hand. Nathan is going to monitor these activity. I probably won't be able to see it when my screen is occupied with the slides, but Nathan will then ask you to speak your question, or you can type it in the chat and he can read it out and we can then move forward. We are recording these lectures. We have done, by the way, the same thing at the end of spring of 2020. Towards the end, because of the pandemic starting that time, this class was also remote synchronous. So we are experienced in these things. So you will have the recording. You will have a something nicer which you don't have otherwise, which is the recording of the lecture to go through and follow up and so on. So, and then at the end of the lecture, we do have office hours. I deliberately keep it that way. I usually hang around with the students in the class. It's much easier to talk about a topic that is refreshed in your mind, and then go through some of these things, right then and there. And I think we'll try to do it the same way over here. Okay, that's the thing. The grading scheme and other things have been set up on the canvas. We are roughly going to have some homeworks spread throughout the semester. We will have a project which will be assigned, probably related set of 2 projects. And then we are going to have a midterm. We will not have a midterm. Instead, we are going to have a term paper. But we'll have a final which will be administered through honor lock. So roughly the distribution of the weightages, etc., is given over there. And talking about the class itself, it's a good mix of theory and projects. You'll see it reflected in the weightages. So roughly 1/3 of the grade of the class is given in terms of the projects. That's a very strong component of this class, which are based on LLVM, which is the compiler that we'll be installing and so on in a few days. And the way the class is positioned is we'll have some introduction of these basic concepts. It might be a while since you did this class. I'm hoping that everybody has done a class which is similar to what we cover here, which is called the front end, which is 4240 in our undergraduate curriculum here. You may not have done 4240 at GT, but probably has done something similar in your undergraduate somewhere else. And 4240, those who have done it know that it means building a full compiler, front end all the way to the code generator. So it has a good bit of project as well. I'm not sure if those who did it outside has a project component. One thing I want to say off the bat right here is that LLVM is a very heavy duty C++ implementation. You have to know C++ very well and be able to navigate large-scale software. So if you have some issues in terms of dealing with code bases, large scale, etc., you may want to think about it. We'll of course provide some help time to time to understand the concepts, etc. But finally, the code navigation and dealing with large-scale C++ is something which is of course expected, is to be already known. And some students who come from more theoretically oriented classes never get to practice compilers, never get to write code, never get to navigate it. And so that's a little bit of an issue. Think about it. You may want to discuss some of this with me during office hours. You may want to refresh your C++ skills, large-scale system skills, etc., etc. You should be able to use makefiles. You should be able to use debuggers and whatnot. As we know, that those are the essentials for dealing with this size of software over here. So these are some of the introductory things. So let us first get going. This is repetition for almost everybody, I am assuming, but it still gives you a very good higher level view. And I'm going to pop some questions in between just to get a feel of what everybody has done and more importantly, what everybody remembers because you might have done some of this earlier. So obviously compiler is a very important technology that translates a source into a target language, and the definition of source and target varies with the compiler. Typically, the most traditional view of compilers is that it takes a higher level language program such as written in C++, Java, Rust, whatever you want to think about, and then converts it into a object or a machine code which is related, which is executed on the hardware or sometimes a virtual machine. This is not necessarily the case always, however, that it translates from a higher level language to the lowest level language. Many compilers work in a manner which is source to source, convert from one source level to the other. And you may ask me, what are the examples of those? So when the compiler technology was in infancy, or which was new for development, for example, C++, when it was introduced, it was converting C++ to C and then piggybacking it on a C compiler. So that's a classic example of a source-to-source translator. Initial versions of C++ compilers did things like that. The second good example could be parallelizing compiler technology. When it was doing parallelization, it used to start with a source program, do parallelization of it, split it up into multiple ones, and then for each one of the programs, it will use the native compiler for serial or sequential compiler to convert it into assembly code, and it will add some synchronization directives through libraries. It will implement those for communication, etc. So that's another source-to-source language. And then at the other end of the spectrum, many times the compilation is also done just in time, JIT. Which you know is the Java bytecode, sometimes converted during execution to assembly or native code, and there are many variants of this which exist at in the dynamic compilation level. Sometimes it is just done ahead of time or just in time. Sometimes it is done during execution. As you know, more and more information gets revealed as you come closer and closer to the execution, and of course it is specific sometimes only to the execution. And so maybe some optimizing decisions could be done better at that particular level. This whole field started a long time back. Historically, IBM did the Fortran compiler, which is still one of the most robust compilers out there. This whole thing is driven, as you know, by a strong foundation in theory, which is the automated theory, the languages controlled as context-free languages, and so on, grammars. So I'm sure all of you has seen this type of a diagram, which is called as the phases of the compiler, which is the next slide here. And we call this as the front end of the compiler. We also called as the language specific part. What it does is it has typically three phases. One is to tokenize the program, or take the program and convert it into a sequence of words. And the process is extremely similar to the way we read books. So as you see in your own mind, when you read the books, you go from one end to the other in a line, you try to use the white spaces or punctuation as the separators of the words. You lump the characters into a word, and then you take that sequence of these characters and recognize it as a word, and then process it in your mind. And so that particular process is mimicked by the scanner. So to group the characters of the program into what we call as tokens of the words, use the delimiters like the punctuation or the white spaces and so on, the commas, is the process of scanner, is the first phase of the compiler. The parser is the one which puts the sequence of tokens and the words together into what we call as a meaningful sentence or a sentential form. So what we have here is, for example, a concept of these words are coming to me one after the other. Do they form something which is valid syntactically or grammatically is the question that is answered by the parser. And this is a very, very important phase of the compiler. Not only it tells us whether the sequence is correct in terms of the order, but it also does something even more important, which you may have already learned about, is takes this sequence and puts a structure on it, or what we call as parses it. What is the meaning of the word parsing? It is to arrange the sequence in a structure, in a hierarchical form, so that then we can assign a certain meaning to it, or we can derive certain meaning out of it. We can go beyond syntax, we can analyze its properties, and so on. And one such example, and that's why I use the word sentential form here, the job of splitting the sentence into sentential form is done by the parser. So what is a sentential form? Sentential form is a part of the sentence. So for example, consider an assignment statement and an expression to be on the right-hand side of the statement. So A is equal to B plus C, for example, is an assignment statement. B plus C is an expression, and it is on the right-hand side of the assignment statement. So B plus C is an expression and is also called a sentential form. Identifier, which is A, is assigned to an expression, is basically how the sentential form looks. And when you feed something called as A is equal to B plus C to the compiler, it first splits it into A and then equal to, and then B, and then plus, and C, and so on. And these are the tokens which flow into the parser. These tokens are then analyzed by the parser and said that, okay, it is good in terms of its structure, but then it converts it into the form, which is identifier is equal to an expression, and B plus C is determined as an expression, and so on. So this process is accomplished by the parser, and it's very important because we want to then deal with B plus C. Is it really well formed? Is it B compatible with C in terms of its type, and so on? And all these decision making has to be done. And that's where we have the third phase of the compiler, which is semantic analysis. And that phase is responsible for taking these bits and pieces which are governed inside a sentential form. For example, B plus C is now analyzed as an expression, and its compatibility, its declaration, etc., are checked. And if it is indeed found to be sound semantically, then this phase is also responsible for generating what we call as an intermediate form or intermediate representation. And together, these phases operate in conjunction with each other, as you have seen by these arrows which are going back and forth, and which generates this intermediate representation by working together in bits and forms of the sentence. And this is called as the front end. This deals, as I mentioned earlier, with the language specificity in terms of there's a grammar which represents the syntax of the language. There is a lexical specification, which represents how each of the words is formed. There are semantic rules which tell us whether what to check, what are the scoping rules, what must be the type compatibility, etc., etc. And all this checking is pretty much what is done by the front end. Now, as you know, this is also something which you must have seen earlier. Typically, the undergraduate classes deal with the front end and teach that in details. However, at Georgia Tech, we also teach a little bit of what goes beyond the front end, which is 4240. What we do there is once this intermediate representation is done, then it's a matter of converting this intermediate representation into the code, the actual code which executes on a given machine, some hardware or a virtual machine, and that is the job of what is called as a backend. And mostly the analysis is done in the front end, reporting of the errors, etc. Some translation is done, as you know, from semantic analysis into the intermediate form. But then in the back end is where this intermediate form, which is machine specific to generating the code, we take this intermediate representation and we generate either an x86 or a MIPS assembly or PowerPC or whatever, or if it's a virtual machine, then the bytecode. This is the one which deals with this particular process. So it's mostly a matter of conversion of this intermediate representation, but it's also coupled very deeply with what we call as optimization. Why this particular coupling? This is because there are so many opportunities to make the code efficient for execution on a given platform. There are machine independent optimizations, which we'll be learning in this class. And towards the end, we'll also learn machine specific optimization. So what is the difference? So the machine independent optimizations try to get rid of certain redundant work in the program, such as unnecessary calculation of certain values, maybe more efficient substitution of one operator by the other. A great example being if you have multiplication by 8, then that is equivalent to a left shift by 3 bits. Those kinds of things are machine independent optimizations typically. But that's not the end of the world. In fact, a lot more opportunity also exists in the machine dependent optimizations, in which you have certain organizations, certain instructions in the machine, for example, which might execute certain operations very, very fast. So for example, if you have multiplication followed by an addition, a multiply accumulate type of an instruction, which may be supported on certain processors, might be very efficient because it saves you the load stores as well as carries out something through chaining in hardware, and that will save you a lot of cycles. So those kinds of things are machine specific or machine dependent optimizations. We'll see a few examples of those also in this particular class. So the focus of this class will be mainly on the intermediate form onwards in terms of doing machine specific and machine independent optimizations. And then before we do that in the rest of the semester, we'll just quickly cover this front end in a little bit of a detail. And I'm going to assign a little bit of reading to refresh some of this from our book. In case there might have been some delay, or you may not have done a proper class with regard to that. So as I mentioned, we have two phases here, scanning and parsing, which are the scanning is converting input text into tokens or words. And typically we do this by using lexical rules of how do we combine these what we call as alphabet. What is really an alphabet? The alphabet is a set of characters that are allowed in a given language. Like, for example, lowercase letters, uppercase letters, certain operators, etc., etc., certain punctuation, commas, semicolons, etc. So those are all alphabet, and we concatenate those, and we form these words. So what rule do we use, for example, to form an identifier or variable name, for example, that is specified here, and things like that. And this particular phase takes these rules, takes the input text, applies it to those, and then finds out if we can find out a longest legal word out of a set of characters. If certain times there are errors here, for example, if we end up using something which is not in the alphabet, that's a clear-cut error. And the other error could be that we cannot really form a word out of certain alphabet, then that could also be an error. We'll see some examples of these a little further. The grammar is, of course, the next thing that is important here, which is used by the parser. And it just tells us the rules of each, how a legal sentence is formed in a given language. There are many kinds of sentences, like control statements, while loops, for loops. They have syntax. Also, assignment statements are core part of it. And we use these grammar rules to take these words, find out if a legal sentence is formed. And of course, we may have syntax error. You have seen these examples earlier. In case some sentence is missing a certain operator or semicolon, or something is in a wrong place in a sentence, you get these kinds of errors. So that's what is done by the parser. And the overall operation of these two phases, let's just learn those quickly. And then we'll move to the things further. So what really happens is the parser is in the control of the overall operation in the front end of the compiler. It demands us, it invokes the scanner and asks it to produce a token. The token is produced by the scanner going through the set of characters, and the token is returned to the parser. And the parser then attempts to match the token of what is expected at the given point in the grammar. If it cannot match the token, obviously it has a syntax error. If it can match it, it will consume it, and then it will just go and get the next token and keeps repeating this. Now, in this process, as you can see, something that is really happening here is one route is you might get a syntax error, and of course that's a meaningless sentence syntactically, and it will not be processed for semantics, etc. But the other route could be hoping that everything is correct. After seeing a set of tokens, we are going to see what we call as a sentential form. And for example, going back to the things which I mentioned earlier in terms of an expression, after seeing a set of identifiers and operators and so on, I will see a sub-expression like a plus b, for example. And at that particular point, I would like to trigger what is called as a semantic check to make sure that A and B are compatible under the additive operator, the plus operator. And so these three tokens and their attributes will be handed over by the parser to the semantic analyzer after seeing a certain sentential form, and it will check it. It will find out if they are sound semantically, and if they are not found compatible, then it will raise semantic error, and then the rest of the program will also not get compiled, but it will catch this error and report and keep going. If it's found compatible, then it will generate the intermediate code from A plus B, as we'll see, and it will keep repeating this process and going through these sentential forms, converting them, again going back and taking up the tokens for the next sentential form, and then checking them for lexically, then syntactically, and then semantically for after seeing certain number of them, and this whole process will repeat, and it will keep generating, if the program is correct, syntactically, semantically, it will keep generating the intermediate representation from it. And at the end of it, once the parse and the program is complete, what you would have generated in the front end is a intermediate representation of this particular input program. A lot of things will get tossed away here, like such as comments, which are not really relevant. Some syntactic sugar, such as commas, etc., which are not meaningful. Some syntactic demarkers, such as semicolons, which act like full stops. They will not get translated into the code. But the rest of each of the sentences will get translated into its representation, and that will be the one which will eventually be used by the backend to do certain things. And there are certain things which will happen in this process, as you know. Once these sub-expressions are found semantically valid, they will be converted into an IR, which typically has a temporary name associated with it. So for example, A plus B, after validating A is compatible with B, will be converted into a T1 is equal to A plus B kind of a form. T1 being the name of the temporary over here, which is holding the result. So this is the overall process of the front end. And in this particular process, we use what very heavily, especially for the semantic actions, we use what is called a symbol table. And the general idea there is in a declarative setting, an entity is declared with its attributes, like, for example, a variable will be declared with its underlying type, etc., scope. And this definition of the variable, the declaration of the variable rather, is valid under a given scope. So it will be held in a symbol table at the point of its declaration. And at the point of its use, it will be looked up through the symbol table mechanism to find out if a variable is declared and what are its types and like scope, etc. And this is called as a binding analysis to determine which A we are talking about here. A is the name of the variable. And once those attributes are there in the symbol table, if they are not there, then obviously it's a semantic error. If they are there, they'll be picked up and they'll be used for doing compatibility checks. So overall, let me stop, take a quick pause here and see if there are any questions on this overall mechanism. You can just raise your hand and Nathan can ask you to speak your question then. Okay, so looks like we are good here so far.
Oh, yeah, someone just raised their hand. Go ahead.
Okay, so are front ends shared across architectures, like compilers made for different architectures? Are the front ends shared and the back ends differ or something like that? Is there a decoupling?
Yes, that's exactly right. So the main idea behind the front end back end separation is that, let's say, if you want to compile C++ onto different targets, we will have the same front end for C++. It will generate the intermediate representation, which will be same. And then there will be different backends, one for x86, one for PowerPC, and so on. Of course, only a part of the backend also will be different, not the whole of it. The machine-independent phases will pretty much be the same. And the code generation and machine-specific optimizations, those phases will change. Great. Any other question? And the reverse is also true. Suppose you want different languages to be compiled on a given architecture, then you'll have just different front ends, one for each, and they will generate the common intermediate representation, but you will share the same backend going for the same architecture. So that's how the separation is clean. Also, another reason for this particular separation is that most of the front end, as you might have seen or built in your undergraduate, is the processes of building front end is very much automated. The scanner, the parsers, and so on. The semantic analyzer is not. That's the only phase which is handcrafted and it differs. But as far as the backend is concerned, it's not automated except for instruction selection phase, which is pretty much the same as similar to the parser. It's a pattern matching phase, and you can generate the instruction selection phases automatically, just like you do the parsing by using tools like Berg and so on. Which you have a template and matching, and you have a corresponding instruction for that. And all it does is pattern matching and generate that particular instruction. But the many other phases like register allocation and certain optimization phases, of course, data flow analysis, etc., those are not automated. Any other questions? Okay, let's move on and let's quickly try to go through this things. So here is the process for tokenization. What is being shown here is a conceptual view of how to group these characters. So there's something called as token buffer, and the scanner is going to read these characters into the token buffer one by one and detect what is called as a termination of a token. What is a termination of a token? So the key idea here is this, that you keep getting these characters one by one till the algorithm knows that they are a part of a single token. And so, for example, this is a simple program. It starts with main here. So first character will be read M. Then we know that the next character that is read is also part of the same token. I is the third one. We don't know if this is a keyword or this is an identifier, but we know that this is a valid token, one of the two. So the algorithm keeps appending these characters as on a longest token basis. And then suddenly it sees this particular opening parenthesis as the token, which is not really a part of any valid token. So there is no token here, MAIN opening parenthesis, all lumped together. And at that particular point, it knows that it has gone too far. It will remove that token, treat the rest of it. It will find out in this particular case that this was an identifier, and in some cases it is declared as a keyword in certain languages. It will declare it as a keyword and return it to the parser. So this is pretty much how the tokenizer will obtain this. And in practice, of course, the scanners are all written, what you call it, as a regular expression. I hope all of you have heard this term and used it also, which is the set of operators plus, star, concatenation, or, etc., which can be used to take this alphabet and form the tokens from them. And through the theory that you must have learned in automated theory or in compilers, there is an automated procedure for taking a regular expression and converting it into NFA, DFA, and then finally that DFA is the one which recognizes and generates this keyword. So in practice, in short, all you do as a compiler writer is write your regular expression which specifies a set of tokens to be derived out of a given language. And the compiler tools like Antler, for example, will generate the scanner automatically for you. Now the parser, as I mentioned, is going to use the set of rules of a grammar. The grammar is written, which is called as context-free grammar, which is used for syntactic analysis. Context-sensitive grammar is not used because it's pretty heavy to use, and for syntactic checking, it is not really needed. So the separation of context sensitivity in terms of checking is delegated to the semantic analyzer. For example, declaration of a value and its use in a given scope is really a job of a context-sensitive grammar. And instead of coding it that way in terms of a context-sensitive grammar and deriving machinery for that, we write the semantic analysis phase by hand. Those of you who must have studied the attribute grammars must have realized this limitation. What is the limitation of an attribute grammar? Not a theoretical limitation, but a practical one. Why is it that we don't use attribute grammars, for example, to derive the context sensitivity in a limited sense? Anybody? Raise your hands, please. You all know probably what is an attribute grammar. Attribute grammar is something which declares attribute of a name, for example, at a declarative setting. Int a means this value a or variable name a is now attached with an attribute int, and in that scope it will flow through and through. And whenever a is used, and when we want to do a type checking on a, we'll use its type, which is int here, and then find out if it is compatible under a particular operation with another type of another variable. So that is attribute grammar, which allows you to propagate these attributes across syntactic rules and bring in the context sensitivity in that particular sense with regard to that name. So the question is, of course, Knuth defined his attribute grammars, and they're beautiful conceptually and very clean to understand the concept of semantic checks, but they're not used. They are not used in that sense, in the grammatical sense, through the machinery of sending these types through different rules and then using them. Why is it that they are not used that way? That was the question. Maybe you can think about it if nobody has an answer so far, and we'll try to revisit in the end if in case anybody has an answer. But so the separation of syntax and semantics is done. Syntax is handled through context-free grammar, and as I mentioned earlier, the parser keeps getting these tokens one by one, and matching them with the expected tokens. And then once it sees a sentential form, it takes the semantic action. So here is a simple grammar which I'm illustrating. It's a very simple, probably meaningless kind of a language, but it has a very simple syntax. It has a main function and it takes some parameters, and then the body of the function has some declaration of the variables. And then we have variable is equal to expression, only one type of a statement, which is an assignment statement. And there are two operators there, plus and minus, and we have two types here, int and float. And of course, this doesn't specify anything about the semantics in terms of whether we can mix them, what is the result of the operation. All this is a part of the semantic specification, which could have been captured through a context-sensitive grammar, but we decided not to take that approach. We decided to capture only the syntax and leave the semantic checking through a different handcrafted mechanism, not even an attribute grammar. So let's see the syntactic operation here of checking this particular simple program, which is shown over here against this particular grammar. So the parser keeps demanding the tokens. The scanner goes and reads this program like this, generates this token, and what the parser says is, okay, I recognize this, and in fact it's in the right place because this particular token is where the program is supposed to start. And so the general algorithm which the parser uses is it starts from a particular place where the program starts, uses a rule which gives you how each program should look like. For example, the rule over here is the first rule, in our where my arrow here, the cursor is, this main opening parenthesis followed by params. This is the starting point of the grammar. That's where every programming this language should look like. And then different programs can vary based on which operators they use, whether or not they use certain number of variables, what they use for declaration, etc., etc. So all that is captured using a single rule, however, and that's where we expect the starting to always occur with the keyword main. So that is what is checked here. And then the parser goes on and keeps demanding the next set of tokens and moves further and repeats this activity. And in this particular process, if it hits a non-terminal or something which needs to be expanded through a particular rule, then it will decide on which rule to use. So for example, in this previous grammar, we have different rules for params here. One rule says that we need not have any parameters. So there could be a program which has no parameters. Other rule says there could be a program which could have one or more of these parameters listed over this particular rule number 3 and 4. And so depending on the program that you are given, the parser will take appropriate action of expanding parameters to either null if it has no parameters, or it will go to the rule number 3 and expand it. If it has only one parameter, then we'll let this var list go to null. If it has two parameters, it will keep expanding var, var, and it will keep doing this expansion as a sufficient number of times to consume all the variables which are declared in this particular params things. So what is this params in curly in these brackets here? This is a non-terminal which must expand using one of the rules, number 2 or number 3. And parser's job is to match the current program. If there is one rule which it finds which can match this input, then it will invoke this particular rule and so on. What if there are multiple rules which match this particular input? Then we call that particular grammar as ambiguous. And that's not right, because it can put different structures on the input for the same program, and that is a bad sign as far as the compiler is concerned for doing further processing. So the grammars are very carefully written to get rid of ambiguity so that there is only one rule which applies and parses it correctly, the inputs. And sometimes there will be no rules, of course, which match the input. In that case, what is the situation? The situation is that if there are no rules found, then the input program has a syntactic error and it will declare it. And the grammar, if it finds a match using a given expansion, then it will try to hone down on that rule and do that particular expansion. The question is, how does the grammar finds out which rule to apply? And again, this leads to the theory of grammars and the theory of parsing in particular. And it does so using what is called as a look ahead. So incoming token tells us that it is going to get matched in this particular way if this route of expansion is followed and the corresponding rules rule is narrowed down using this particular look ahead, which it tells us to which route to go on. And for that particular matter, we have classification of these programming language grammars into LL1, LL2, LL3, LL4, which means one token is sufficient to narrow down the rule. Sometimes we are not sufficient to use only one token. We need two tokens. So LL2 is in that category. But no more than two tokens are needed to narrow down a given rule in any setting of the program. Sometimes 3 are needed, but no more than 3 are needed, so LL3 and so on. And sometimes we do have sets of grammars in which the grammar is not even LLK for any K. What does it mean? That means that even if we fix a k to a very large number, let's say 1000, we can always find a program which cannot disambiguate the unique selection of the rule, and that means this particular language is not LLK. And for those matters, we have to now go to a different set of grammars and rules, which are called as LR0 or SLR1, SLR2, in which the look ahead is not generated on the left-hand side of the sentence, but is on the right-hand side of the sentence. So let's get into some of that discussion in a minute. In this particular case, we have this particular grammar, which is LL1, because by looking at the next token, I'm able to figure out where I'm going next, which rule I'm going to use, that, and so on. Consuming main, I go further, I get my next token, and again, the same activity happens on the scanner side. It will generate the token, which is open parenthesis, and the parser is continuing the expansion on the right-hand side. It will match it to the open par, and it will then continue. Now, the next token that it gets here, and this is where it is interesting, as you can see here, from the scanner, it gets closing parenthesis. So the parser asks this question that how can I match it? Can I match it using expansion of parameters to null or to something else? So you can see that the parser is intelligent here. If it expands parameters to null, then the closing parenthesis can be matched by using the token name which is following the parameters in the set of rule that is being shown here. However, if the parameters had expanded using var, which was the other alternative, it could not have matched it. They would have led to a mismatch. So the parameters are expanded to null very intelligently by this particular grammar or the parser, and which leads to the closing parenthesis getting matched. And the process then continues in terms of by matching the rest of the tokens, which I'm not going to get into. So in this case, we are able to uniquely show that by looking at closing parenthesis, we are able to let parameters go to null or parameter go to the other expansion, which is var. So with the input token where var, parameters would have been expanded to var, that particular rule beginning with var. If the input token is closing parent, however, the parameters are nullified here in this particular rule. What if the incoming token is anything other than close par or var? Anybody? Then what would happen in that particular case? We are at the potential point in the parse where parameters is being expanded, and the incoming token is neither close par, okay, not neither closing parenthesis, it is nor variable either. So what would happen?
Syntax error?
Yes, exactly. Because if something is other than these two, it means that the token is in a wrong place. There is no expansion of parameters which can lead to its matching, and that's a syntax error. So what will happen in case there are syntax errors? The parser will try to repair the program. It won't repair it for you so that you can actually derive a meaningful program out of it, but it will discard the token or do some repair-y kind of algorithms. And what is the goal there? The main goal is to be able to catch as many errors as possible in one go. And all the syntax errors will be reported there, and then the parser will keep moving on. Generation of repair-y is a very important attribute because you want to catch all the errors and show it to the programmer in one shot, because the productivity of the programmer really depends on the ability of the compiler to report as many errors in one go as possible. So we have, of course, a syntactically correct program here, and the rest of the animation keeps showing what tokens are coming in, how they are being matched. For example, in the next step here, the main body expands, which is non-terminal that we need to expand, and the incoming token exactly gets matched as a curly opening parenthesis and so on. So in short, in terms of parsing algorithm, the incoming token or tokens sometimes, if the grammar is LL2 or LL3 or whatever, tells us which exactly the rule to use. By the way, LL grammars, as you know, are what is called as the top-down parsing grammars, and they all try to do this expansion from the start symbol of the grammar, which is C program here, by using the rules so that they can match the incoming token by using or developing what is called as the left context of the sentential form. So you can see that in C program, all these main, open pair, parameters, close pair, they all have been matched here. And next thing that we are trying to match now is main body. And we are doing what is called as the leftmost match here. So given the left context and the incoming token, if we are able to predict exactly one rule using the incoming token or tokens, then the particular grammar is called as LLK for that particular K. Here it is LL1. Many times, as I mentioned, we may not be able to do even any grammar which is LLK for any K because we won't have a unique choice of a expansion of a non-terminal. And in that case, we'll have to resort to the different grammars which are expanded or rather reduced from the right-hand side, and those are called as LR grammars. And again, if you can do it using one token, it is LR1. If you have to do it using two, LR2, etc., etc. Can somebody think of or give me an example of a grammar which faces a problem of not being LLK? And there's a very classic problem here in programming languages, a construct rather, which creates this particular problem, and which leads to a grammar not being LLK for any K. Okay, anybody? Okay, as you watch these videos later, think of these questions and seek some answers to those. And as you read through the pacing material, I'll give out the answer for this one. This problem is called as dangling else. And the nested loop, nested if then else's, we can deeply nest them as much as possible and fool the grammar for not being LLK, because the next one we don't know if it is if then which has terminated or if it's going to have an else clause in it. So that's a grammar which is not LLK for any K. Moving on, I will let you do the rest of the animation. I'll skip through it. And this grammar keeps nicely chugging along like this. And each sentence or sentential form, it matches and keeps going further. For example, it's going now to the assignment statement, going to equal to expression, and it will consume the rest of the stuff. And at the end of this, it will have completely matched the program with the C program, and that would have led to a successful parse. Of course, as I mentioned, if our only idea were to generate syntax errors or not and stop there, this would work perfectly. But what really happens here is once we consume a part of the sentence or match it rather successfully, our next goal would be to check its semantics. And so after each of the small points here or steps here, we will call the semantic actions, and they will step in and check the semantics of the part of the program that is seen thus far. So for example, after doing int AB, our goal would be to convert this A and B into an internal symbol table representation so as to hold their attributes, and then during A is equal to B, use those attributes to find out if A is compatible with B. So in short, for doing this, we have the notion of symbol tables, and where we hold these attributes. So semantic actions get triggered in terms of insertion of values into the symbol table, and then the semantic checks takes place of taking those values out of symbol table and trying to find out the values are compatible or not. As I mentioned, int AB declares A and B within the current scope, type integer. At the end of processing this integer, declaration, which is int AB, we should see this type of internal representation called symbol table. And you can think of this representation as also a kind of an IR, because it is holding this particular information in a certain way. As you can see here, we are doing it for each name, holding the attributes like its type, its scope, etc., etc. So typical semantic actions are to enter these into the symbol table, and then during the processing of this rest of the program, like A is equal to B, look up the things in the symbol table, find out which is the binding of each one of these variables. That is, when I'm doing this A here in this expression A plus B plus C, is this the A which is declared in which scope? The nested scopes and scoping rules have certain different A's that could be declared, and block structure typically says that the innermost visible one is the one which we have here. So determining these bindings through symbol table is one very, very important aspect. Holding the information is another key aspect at the point of declaration. And then doing the checks is yet another aspect. And then the last aspect of the front end, as I mentioned, is once the check is passed between A plus B, for example, is to what we call as allocation of a temporary. So here, what is this temporary name? So this is really a intermediate value which is generated by A plus B, held in some abstract name T1 introduced by the compiler. Compiler makes sure that, of course, none of these names clash with the user-defined names. So that's why they might certainly start with a symbol, dollar symbol, or underscore, etc., in which the user-defined names cannot start with those. So the namespace of temporaries is different and distinct with the user-defined names. And they're typically generated as an artifact of semantic processing to hold the intermediate values, and are propagating the information from one statement to the other by breaking down these expressions such as T1 is equal to A plus B, and then T2 is equal to T1 plus C, and so on. So how is this semantic actions typically get triggered? So there are two ways to do this, and different compilers do it differently. The modern compilers do it in a different way. Conceptually, this is easiest to understand, what is called as an action symbol, which is embedded in the grammar. So what it tells us is that after seeing a certain amount of syntactic context, we need to do its semantic processing. That's what this action symbol first of all tells us. And then these action symbols are associated with a procedure which will take these different values that are seen, and it will act on it, and it will implement the semantic actions. So let's see those just in a very quick manner here. So what we have is a declarative statement which has a type information. And as you can see here, after that type information, there is a variable list which it has. And that variable list will expand to a list of one or more variables. And the type, of course, will be int or float. So that's the basic grammar. Ignore all the hash symbols for a minute now. So the basic grammar tells us this is how the syntax of this language looks like. Now, what is it that this semantic processes procedures are trying to do now? Well, its goal is to take this program, which is declared like this type followed by the list of variables, and convert it into a symbol table representation through what is called as a do declaration procedure, which is being shown at the bottom of the screen. You have a type followed by 3 IDs, and you want to take those and you want to associate this type with each of the IDs and in the current scope, which is randomly called as scope 3 here. So how does it do it? Incrementally or step by step. After seeing type, what it does is it invokes what is called as a put type procedure. And it's building it what is called as an association stack or a semantic stack of the names and the types. So separate stack is built here on the left hand side, as you see. Put the type as at the bottom of the stack, and that's all put type does. Now next we go into var list. The var list will expand further. By the way, the put type will know exactly which type it is at the point of the type being parsed, because it will be either int or float, and it will save it at the bottom of the stack. Next, when it goes to var list, it will go to a single variable add declaration, and it will pick up the exact name of the variable, etc., and build the records there like ID1, ID2, ID3, and it will try to associate them with each other. You may ask me this question that why is association needed, etc. Well, certain languages have some weird features of nested declarations and so on. So it is to keep track of which variable is associated with which type. So that is the precaution here, which is being taken in the semantic stack. So each of these add declarations will keep track of these. And then finally, we'll have at the end of all these building of this chain will invoke these do declarations, and these do declarations will take this whole semantic stack with the association list that is being generated, and it will convert it into an internal representation shown in the symbol table. So these are the semantic actions that are associated and with the action symbols. Each one of these are action symbols: put type, do declaration, add declaration, process declaration. These are all action symbols which are calls to the semantic analysis functions or procedures, which will pick up the information and which will do this incremental stuff on the semantic stack. And then eventually, after seeing the whole semantic context of the complete declarative statement, you can see that the do declarations is the one which is doing final processing, taking that and converting it into the particular symbol table over here. Semantic actions, as I mentioned, one of them was about insertion of all this information into the symbol table. Second one was about the checking, which is to look this up in the symbol table, find out which is this particular variable called as through binding analysis, and do the type compatibility checks, scope checks, etc. And then once the checks are passed, trigger a translation, which is to generate the intermediate representation, like the way I showed. Basically, through this T1 is this is the intermediate representation, which is what is called as a quad representation, a classic representation used by the compilers in almost all the settings, including LLVM, because it has 4 fields: the target, the assignment operator, the and of course is implicit, and operand 1, operand 2, and operator. So there are 4 fields like that. One associated with the leftmost variable, 2 operands, and the operator which is embedded here. So this is easy to understand in terms of how the semantic actions or action symbols get embedded. But the real world compilers, what they do is first build the parse trees and then traverse the parse trees as you had done in 40to40, traverse them, check their semantic legality, and then emit the intermediate representation from there. And they do not involve action symbols like the way it is shown here. So the representation that is used, even before we get into the quad trees, is sometimes called as the AST, or abstract syntax tree, which is yet another form of an intermediate representation, which is used by the compilers for doing the abstract syntax checks, the semantic checks, and then converting them into the operational one, which is why do we have, of course, a quad representation? That may be one question that comes to your mind. The answer is very simple. Most of the machine formats, instruction formats, have 4 fields. Some of them have lesser number of fields. Some of them could have more number of fields, but most of them have 4 fields, combining 2 operands, generating a result out of them. And that's why this is a desired implementation. So here is the complete compiler structure: scanner, parser, semantic actions in the front end, and the code generation, and generating the final assembly out of it is the thing. So to summarize, what we have here is a front end, back end split between the compiler, and we will not be using any front-end knowledge in this class, but you should definitely refresh it. I'm going to send a list of topics to be read on your own from the current book, just to refresh that. There are many things which we have skipped here, which I want you to kind of absorb while you do this quickly in terms of reading. One of which is this, that why do we have a concept of LLK or LRK type of language? Why not just deal with the whole gamut of the context-free grammars? And the languages? Go ahead.
Sorry, I guess I should have raised my hand. But yeah,
No problem. Go ahead.
I guess you want the parsing to be tractable, as in, like, you don't want it to be unbounded in terms of time.
Good answer. Good answer. So basically, the main reason is this, that those of you might be familiar with the theory of languages. The general class of CFLs, the context-free languages, is parsable, but it is not parsable in a deterministic sense. In other words, you may have to go forward, you may reach a dead end, you may have to go back, try yet another route, yet another rule, and you have to keep doing this. And if this is the case, then the parsing time will explode like anything, and we will be spending a lot of time in just doing parsing. Remember, all this particular development occurred when the machines were pretty nascent, like PDP-11. Even on the modern ones, with the scale of the programs that we tackle, the budget for parsing is kept very small. The parsing scanning budget is no more than 10 to 12%, because the rest of the budget is to be split between semantic analysis and mainly on the backend side. And the compiler is a very interactive tool, so that is why we limit ourselves to a subset which is deterministic, in which we are sure that once we choose a rule, either that rule will lead to a successful parse or it will lead to a syntax error. Both outcomes are, of course, they are dependent on the input program. But it will never be that we'll try one route, we'll go forward thinking, hey, this is a great rule, we should try it, and keep going deep down the so many taking tokens and so on, and then finally reach a dead end and say, hey, no, this wasn't the right one. This has led to a syntax error. Oh, maybe this wasn't the only route. Let's go back all the way. Let's try yet another one. If you're in that kind of situation, this is a non-deterministic parsing, and that will lead to a huge compilation time, and that's not something which is a good design principle. And fortunately, most of the language, etc., especially the syntax side of it, can be easily captured by keeping ourselves within the realm of LLK or LRK parsers. The production parsers for most of the languages are LR1 or LR2. The other question that comes to our mind in front-end side is, why bottom-up parsing? I think I already gave out the answer, because many constructs are not LLK for any K, like dangling else. And the second one is, if you've seen the way things operate here, And if you read a little bit about SLR1, LR1 parsing, what we do is we expose the right context, and we are able to see all the parts of the sentential form, and we are able to do some quick analysis on them in terms of a reduction, and choose in terms of checking their semantic compatibility, etc., because pretty much the whole sentence is exposed. So from an efficiency standpoint as well, and implementation, the LR parser or the bottom-up parsers are very important. The attributes in the attribute grammar flow mostly upwards, synthesize attributes. So what I mean by that is if A plus B is fully exposed, we know that the type which T1 is going to get is dependent on A and B. Like if it's adding int and float, it will get float, for example. And this won't be known unless we have the full sentence exposed. So this is another reason why we have LR parsing as a production parsers. Antler is typically the tool which is used for generating these parsers automatically. So what is it in this particular class? Let's talk about it, given just almost the end of the lecture.
Real quick, Professor, while we were on the topic of efficiency, there was a question about whether front ends could be designed to work in parallel.
Yeah, so I think we certainly can, and there have been efforts to separate out the set of rules which could be explored in parallels and commit them together, etc. However, it's the you can see that it's an inherently process which is sort of carefully kept under control based on the expressivity that we might lose if we go for natural languages, for example, which is not really CFL. So one extreme end is not even CFL, which is useful to us, natural languages. The one which is useful to us is carefully controlled by keeping it LL1 and LRK. And some few gains are there within these useful games. So I will answer the question in terms of the useful domain. There might be small speed ups here and there, but it's really not needed per se, given the fact that it's kept under control by carefully choosing the syntactic details of by the design of the language. The other end, which is of course natural languages, yes, but a very different strategy is used there, which is based on ML and so on in terms of pattern matching and deriving the meaning of the sentence. Google, for example, uses none of these heavy-duty technology to understand natural languages, but relies on very heavy-duty big data. And that's a completely separate discussion. That's the answer, I guess. So coming back to just to wrap up a few things. So what is it in this particular class going forward? So we are going to see how the properties of intermediate code are so interesting in terms of what is called as a core property of data flow, of how values go from one IR statement to the other. We'll also analyze the control flow of the program in terms of the structures, the loops, how they look, etc., etc., and how can we do the analysis of these to do certain optimizations. So that's the first topic. Second one, we'll see that how some of it is unified and in fact made even better by SSA. What do you mean by better? The better means in terms of compilation time, things become faster in SSA sense, and many optimizations could be done using one which replaces multiple phases of the optimizer. Then we'll go into data dependence, which is a topic of different relation in the program between different statements in terms of the constraints. This is not about flow of value, but constraints. And we'll see how to optimize loops, etc. And then we'll visit some traditional topics going into more advanced techniques, register allocation, and instruction scheduling, especially for machine-specific optimizations, etc. And in between, this is a very high-level overview, but we'll see many properties, what I call generally as a trade-off between safety and precision. of analysis. So what the compiler infers from a program determines its ability to restructure it, because the restructuring is really helpful. For example, can I move this statement out of the loop? If I can, then it executes only once, otherwise it executes billions of times inside the loop. So can I move it out is the real question. And the answer to that really depends on the precision of analysis the compiler is able to give. That in turn depends on the analysis techniques, how deep they are, what they use. It also depends on language properties like pointers, etc., which might be prohibitive in terms of reasoning at static time. So all these trade-offs between safety and precision determine the efficiency of the compiler, and we'll be mainly seeing all of these, and of course its use in doing optimizations and improving the performance of the program. So I better stop here. Sorry to go a little bit over, but this is recorded, and you can of course revisit some of my questions and your answers to them. Perhaps you can chime in next time to give the answers. I'll be the follow-up from the next lecture. We'll be starting with the intermediate representations, and we'll be diving into the analysis of the same. And we'll also talk about conversion of first intermediate statement, which is AST, to intermediate forms. And in between, like after today or probably tomorrow, I'll be sending out the list on announcements about the topics to be read. Try to read them rapidly. You don't have to get into in depth. They're not on the exam. They're not a part of this class, but this is to just warm up for this class. Thank you. And in about 5 minutes, I will join the office hours. Thank you very much.